So did you think about this question? So it's about a survey as a whole, and X bar is the average from the survey. Is it random? The answer is yes, because if you repeat the survey again, then you're going to get a different set of 1,000 people. So their annual incomes will be different, and so X bar will be different. If you even though the if you, even though if your survey was correctly designed, two surveys should be similar to each other, but it cannot be exactly the same. And of course, the some of the survey respondents may overlap, but in general they must be different. So X bar is random by the same rationale as I explained in the first question. So if you repeat the survey, you are going to get a different X bar. That's that's the basic idea of a random object. So we like this is what we are going to study in this chapter. The randomness in X bar. The X bar is our main object in this chapter, and its randomness is coming from not just choosing one random person. It is coming from choosing 1,000 people as a unit or as just as a set. So you have the underlying experiment in here is just one experiment is one survey. So choosing 1,000 people is one experiment, right? In the earlier example, one experiment included only one person. And so if you chose 1,000 people at random, it means you are doing 1,000 experiments. But now it is choosing 1,000 people is just one experiment. And the result of the experiment is just one average, X bar. Okay, that's what we are going to study in this chapter. It's a little bit change of the scope. The scale of randomness is totally different from the previous chapters because we have to think about data, not just one single observation or one observation of a random variable. So we formally define a random sample. A random sample is a collection of observations satisfying these two assumptions. Have to satisfy these two assumptions. And usually a random sample is denoted by x1, x2, up to xn. It's a set. So, and there are n number of observations, n number of random variables, and n denotes the size of the sample size, right? So, in the previous chapters, we understood this random sample as a repetition of one single experiment for n times. But now, from now on, we are going to treat this set as just one result, one repetition. It is just one repetition. One repetition generates n observations. That's the major difference. And a random sample has to satisfy two assumptions. The first assumption is identical distribution. So all observations should have the same distribution. Like, for example, the mean of the first one and the mean of the second one has to be the same. And like not only the mean, like variance, probability, median, everything, they are from the same distribution. So the distribution of x1 and the distribution of x2 must be the same. It's almost always it's automatically satisfied. Like it's hard to make up a counterexample. For example, if you imagine a very absurd example where x1 is the first person's annual income and say x2 is the second person's height. Eh? Of course, they have different distributions, but no stupid guy would do like that kind of survey. So, like if X1 is from the distribution of, like say, income distribution, and X2 is from like say height distribution, and the next one is from say like weight distribution, and then of course the distributions are different, which breaks the first assumption, but it's usually maintained. And again, the point is the mean is the same or the variance is the same. The mean and the variance are the same at the same time. And the second assumption is actually more important and more often violated. So the second assumption is the independence. Statistical independence we learned in chapter 2. That means all observations must be independent of each other. In other words, the result of the first observation does not affect the following or any other observations, any other random variables. It's We have studied independence in chapter 2, and you may remember what we have done and pretty much the an intuitive definition. So x1 and x2 are independent. For example, when you choose, say if you like when you survey one person, let's say and ask his uh, annual income, and if you ask just the next person to him, then she may be his wife. Then if you ask the same question to her, then the first person's annual income must be the same as the second person's income. In that case, independence breaks down. So when you ask one person, then the second person must be totally new person, newly randomly chosen person. So, and I am going to assume these two assumptions like throughout the end of this semester. So relaxing these two assumptions is very like it's very hard. So I'm going to maintain them in this course. And many major statistics materials assume these two assumptions in general at even at a higher level. So then, in our example, to compare, to understand the meaning using our example, in the previous chapters, we learned that one experiment generates one observation. So that's how we defined an experiment and how we defined a random variable. And we repeat the experiment many times, and then by repeating the experiment many times, we have a distribution. So each time the outcome may be different. So after collecting all the outcomes, you can see the distribution. That was the approach in the previous chapters. But in this chapter and in the following chapters, our main focus is on the random sampling. So generating a random sample is random sampling. So the experiment is a random sampling, generating a random sample. So one experiment generates n observations, a random sample of size n, and then from the sample calculate the mean, the average x bar. This you may understand these two steps as one experiment. So one experiment includes generating a random sample and calculating something from those n observations. And you get one number which corresponds to x bar in this case. And you repeat the random sampling, repeat the experiment, which means you have to resample everyone. Resample. That's repetitions. And then we are going to learn the distribution of x bar. X bar, the average annual income can be different from one survey to another survey. So there must be distribution. It is random. So there must be distribution of that, and we can calculate the mean, the variance, the probability. So that's what we're going to do in this chapter. Um, and so again, examples. There are, so hypothetically, you have to imagine something like this. In our example, one research center conducted one survey of 1,000 people. To repeat that, you have to imagine 100 research centers. Suppose that there are 100 research centers who are doing the same research. All of them are studying the average annual income. So each of them surveys 1,000 people and reports their average income. Uh, that will make 100 observations. So one observation from one research center or from one survey. So there will be 100 observations, and they are, even though 100 observations would be similar to each other, but they are not exactly the same. So there must be some distribution, which is the sampling distribution. We say the distribution of x bar is the sampling distribution because this is generated from the experiment of random sampling. So it is a sampling distribution. And we are going to, as I said, we are going to consider what's the mean and variance of x bar, what is the probability distribution of x bar, how can we know that, um, and the result is the answers to them are very surprising because it's purely hypothetical repetition. It's very hard to repeat the survey this many times, but without the repetitions, still we know the distribution. We can calculate these guys without repeating the surveys. You are going to see them at the end of this slide. By the way, uh, I want to explain this confusing point like briefly. So X bar in our example, X bar is the average annual income from a survey, like say 1,000 people. So it is random, but it is a mean. It's an average. So it is a mean calculated from the sample of 1,000 people. So it is a sample mean, but it is random, as we saw. So it is random. So we can think of an expectation for a random object. So the same here. The sample mean is random, so we can think about the mean of the sample mean because every random variable has its mean. So this is the mean of this guy, which happens to be named as a sample mean. So expected value of x bar is the mean of a sample mean. So because of this confusion, I am going to call them x bar as the sample average or simply the average because average sounds more like kind of like computable, like calculatable, something you calculate from the sample. But I am going to call the mean of the sample mean as the expected value or expectation of the average because expectation sounds more like a theoretical object. Expectation is not something like you can calculate, but it's more like mathematical thing or like just imaginary, conceptual object. So I'm going to call this the expectation of the average. But it is not wrong even if you say it's a mean of a sample mean. It's a population mean of the sample mean. True mean of the sample mean. It's confusing. So okay, in the next slide, I am going to consider a simple example to study the sampling distribution. So I think, as I said, this chapter will be short, but it's super important, and I just want you to uh, understand the main idea and like to prevent confusion in the future. It's very confusing, can be very confusing. You know, See you in the next video.